So chapter 3 of this textbook is all about numerically organizing data. So before we had visually organized data in our frequency distributions and our relative frequency distributions. And now we're actually going to start computing stuff through different types of measures of these numbers. So like I said, you will be using Excel in this course. I looked through the notes for 3.1, and actually not today, but next class you will. Okay, the first measure of central tendency, which honestly, the measures of central tendency we're going to go over today are going to sound very familiar to you, but I'm going to make them complicated, is called the arithmetic mean of a variable. The arithmetic mean of a variable is computed by adding all of the values of the variable in the data and dividing by the number of observations. You would have casually called this the average. Okay, it's the same idea as the average or the mean of the data, but we're making it statistics, so it's called an arithmetic mean. There's two ways to calculate mean. They're really the same formula, but the variables change. If you're dealing with an entire population, the population mean is represented by the Greek letter mu. Everybody say mu. That's the Greek letter mu. And it is computed using all of the individuals in a population. That means that population is a parameter because it uses all. So we have our formula here. There's going to be two ways you see it. Mu is equal to adding up all of your observations, dividing by the number of observations. Or we can write that more simply as the sum of the observations over big N. Thank you. So that weird giant E looking thing is a sum symbol. It means add all of the things up. So if you ever see that, we're talking about the sum of something. If you're dealing with a samples arithmetic mean, this time we change the variable. It's now x bar. So it's literally an x with a bar on top of it, pronounced x bar, which is nice. It is the same exact thing. It is used when we're finding samples arithmetic mean. That means it's a statistic. So we have the equations here. Same vibe, that x bar is equal to adding up all of the observations and divide by the number in your sample. Remember, this is a sample instead of the entire population. Or the sum symbol, the sum of all the observations divided by the number of observations. Those are our two formulas for mean, but again, you would have casually called these things an average before today. So we're going to go ahead and jump. Oh yeah, there's a nice little FYI right here. FYI, we generally round mu and x bar to one more decimal place than the raw data. So immediately, we're using whole numbers here, which means our answer for mu will be like one decimal, because we're using one more decimal than the data. And so if we don't have any decimals showing, you give me one decimal. That's a general rule. Make sure you read the instructions for how it wants you to round, but that's the general rule. So the data in Table 1 represents the first exam score of 10 students enrolled in introductory statistics. These are not your scores. These are fake people. Treat the 10 students as a population, and we want to compute the population mean. That means that we are doing mu equal to the sum of all of the scores. So yes, we're going to add them all up. And I know eventually you're just going to type those into a calculator, but because these are our notes and we are learning, let's show all of our work. So we're going to do 82 plus 77 plus 90 plus 71 plus 62 plus 68 plus 74 plus 84. Oh my gosh, I didn't make my line long enough. Plus 94 plus 88. So we add all of those together. And we're going to divide by the population total. And so the number of people in this course, based on Table 1, is 10 people. And so we compute that. In your calculator, if you grabbed it, go ahead and do 82 plus 77 plus 90 plus 71 plus 62 plus 68 plus 74, 84, 94, and 88. Press Enter, then divide that by 10. I'll give you a second. 79, but remember, we're going to report our sample means, or our, population means to one more decimal, so we're going to do 79.0. I know that doesn't feel like a difference, but let's get into the habit of always making sure we're reporting one more decimal than the raw data. Cool, great. So that is the average of the entire population. That is the arithmetic mean for the population. But now we want to find a simple random sample of size 4 students using our calculator and a seed set at 4. So let's review those steps. How do we set the seed? Yeah, you put the 4. Okay, great. Store. Math. Probability. 1 because it says rand. Yeah, so we're setting the seed at 4. Press enter. Now, how do you actually pull that simple random sample? Math. Probability. Okay. And then how do you fill that in? Yeah, so the lowest number, the highest number. What sample size do we want? 4. So we're going to go 0, then 10, or sorry, 1, then 10, then 4. Yeah. And so it should say rand int no repeat 1, 10, 4, correct? Yes. And when you pull that, what 4 numbers does it give you?
10, 5, 9, and 8.
Should be 4, 9, and 8? No? Is it 5?
Yeah.
Oh, LOL. Okay, that means my key is wrong, and that's fine. So we get 10, 5, 9, and 8, which is going to be Juan, Jennifer, Justine, and Sam.
Miss Quigley, I would appreciate one of the names you picked.
What? Which one?
Which one? You're not funny. You're not funny. We'll have a discussion about this later.
Okay, this is out of the textbook. Don't blame me.
That name has to be removed from the textbook.
Okay. So here's our sample. Our sample that we're pulling out of this population is Juan, Jennifer, Justine, and Sam. We're going to compute the mean of the sample found in part B. So now we're computing X bar. Since we are computing from a sample, I don't use mu as the variable for my mean. I use X bar. And all I have to do is add together Juan, Jennifer, Justine, and Sam's averages, which is 88 plus 62 plus 94 plus 84. And this time I'm dividing it by how many? 4. Easy enough. What do we get this time? 82.0. Now this is an interesting moment. What was our population mean? 79. What was our sample mean?
82.
Now those are close. But because we're pulling a sample instead of using the entire population, our data is not as accurate, which is why we spent all that time in chapter 1 talking about pulling correct samples, sample sizes to make good conclusions so that we're using as much data as efficiently as possible. But it's just cool to see the difference between mu and X bar here. Are there any major questions about mean? With mean? Yes. Now, if you think back to 8th grade math, you learned about 3 things. It was like mean, something, and something. Median and mode. Guess what? We're doing the same thing today. Those are all called measures of central tendency. So on the next page here, we're going to start talking about the median of a value of a variable. So you do know some things about this. The median of a variable is the value that lies in the middle of the data when arranged in ascending order. We're going to use capital M to represent the median, not lowercase m specifically, it's capital M. So to find the median, you're going to arrange the data in ascending order and determine the number of observations. Determine the observation in the middle of the data set. The reason you want to know the number of observations is because if the number of observations is odd, then you know exactly the correct answer. It's whatever one is actually in the middle. But if your number of observation is even, you're going to take the 2 in the middle and then find the mean of them. So you're going to add those together, divide by 2, which is all things you learned in 8th grade math, you just might have forgotten. So this data in table 2 represents the length in seconds of a random sample of songs released in the 1970s. Find the median length of the songs. Okay. Is that on there? Our family is on there. Cute. Okay, so what we're going to do is we're going to list the lengths from least to greatest. What is the shortest song on there? 179. What's the next shortest song? 201. So what I like to do when I'm doing this is I like to mark them out. Don't make it too dark in case you need the number later. But like that way, kind of like when we did the frequency table, I saw some of you doing this. This is a good idea. After 201, what's up next? 206. And then 208, 217, next, 222, then we had 240, then we have 257, and then 284. We are listing them. I just ran out of space. You can make your list up and down. I just chose to do it this way. Okay, cool. Now, the way I like to do median is probably the way you did it in 8th grade. Let's just like cross one off from the top and the bottom of our list until we arrive at either the 2 in the center or the 1 in the center. That's what our math is telling us in that definition page up there. So again, don't mark them off too much in case you need the numbers later, but if we mark off the highest and the lowest, and then the next highest and the next lowest, and then we keep doing that process until we're left with either 1 or 2 in the center, which then tells me that the median for song length is 217. Easy peasy, right? Things we know how to do. Let's find the median of the data in table 1, which, annoying, you're going to have to flip your page back and forth. So sorry. But if you look at the table 1, which is the test scores, what was the lowest test score? 62. And then the next lowest? I know. If you just list them out, I'll write them down and then we can switch.
62, 68.
Okay.
71.
Yep.
74.
Yep.
77.
Yep.
82.
Yep.
84.
Mm-hmm.
88. 90. 94.
Very good. Okay, so we've got this whole list. I'll let you write it down in case you were flipping back and forth. Okay, then we start marking them off from top and bottom. So we get rid of the highest and the lowest. Again, don't mark them off too heavy in case we need this raw data back. And we just keep marking them off. And then, there's 2 in the center.
Oh, no.
There's not actually 1 number in the center. There's 2. So what we do is we find the median by taking those 2 numbers and computing the mean of the 2 central numbers, which means we're going to add them together, divide by 2. 77 plus 88 divided by 2 is going to be 79.5. I just stuttered over all of those words. I said 88?
Yeah.
My bad. 82. Now before you flip, we are going to be able to do mean and median on our calculator. And because the data sets that we're working with today are small, we are going to practice them on our calculator. I will show you next class how to get this sort of thing on Excel because we're going to be starting to work with bigger data sets that are going to be annoying to type into your calculator. So everybody right now, we're going to follow these steps here to find the median of, I believe this is the table 1. Okay, we're going to go to stat and we're going to go to edit. If there's anything in your calculator, just press second plus 712 and get rid of it because AP took a test this morning and changed all of your settings anyways. Second plus 712. But we're going to enter the entire raw data into L1 and L1 only. So that means I'm putting 62 enter, 68 enter, 71, 74, 77, 82, 84, 88, 90, and 94. So I'm entirely in L1 on the stat edit screen. Once you have that there's not coordinate points, so we don't need to enter anything into L2. We only have single data, so we're only using the first list. Do I need to pause?
Yeah.
Okay, sorry. They're all typed in. We press stat again, and we go over to calculate. Now, this menu, you've always politely ignored this first option for your entire life. What does that first option say? 1 var stats. How many variables are we using in this equation? 1 variable. So we're choosing that first option that says 1 variable stats. That's your new button for today, 1 variable stats. Your option there asks you, well, what list did you take this data from? Well, we put it in L1, so we make sure L1 is typed there. It probably is. You go down to calculate and you press enter, and it's going to show you a whole list of things here. The problem is you have to remember what you were computing. So if we were looking for the arithmetic mean, That was X bar. So that was from the other page. We got 79 when we did this. And then this last question, we did the median, which if you scroll down is the MED median. Yeah, so you just make sure L1 is there at your list since that's where you put it. And then it tells you all the data. I'm eventually going to teach you what all the rest of these numbers mean and what they do. But today we have the mean and the median. Niate, did you have a question? Sound cool? For smaller data sets, it's probably easier just to do it by hand, but eventually you're going to want some help in doing these sorts of things. Now, one of the central ideas of looking at data and looking at statistics in a good way is to make sure you understand the concept of statistics being resistant. Here's a new vocabulary word for us today. Which measure of central tendency is better to use? The mean or the median? And it totally depends. A numerical summary of data is said to be resistant if extreme observations, so super big or super small relative to the data, do not affect its value substantially. So the median is resistant while the mean is not resistant. And let me show you why. This is a very interesting question. Yolanda wants to know how much time she typically spends on her cell phone. She goes to her phone's website and records the call length for a random sample of 12 calls that is shown in Table 3. Find the mean and median length of a cell phone call, and which measure of central tendency better describes the length of a typical phone call. So here we go. Now, this is a sample, so to find the mean, do I use X bar or mu? X bar is for a sample. So when we're finding the mean of a sample, that's X bar. But I'm going to do just like we did before. I'm going to add up all the cell phone calls. So 1 plus 7 plus 4 plus 1 plus 2 plus 4 plus 3 plus 48 plus 3 plus 5 plus 3 again, and then plus 6. Obviously, I know you can do this eventually just straight to your calculator, but these are our notes. We want to make sure we know what we're doing later. And the sample she chose was 12 calls. So I'm going to add those all up, divide by 12, and report back what I get. What is the average length of one of her phone calls? 7.25, so 7.3, 1 decimal more than our raw data. Our raw data was whole numbers. Okay, interesting. So now let's find the median. Median is represented by big M. The median, we just need to list them all in order and then figure out which one's in the center. So if we do the listing of the order first, I like to put mine in a set, which is 1, 1, 2. There was 3 3s, 2 4s, a 5, a 6, a 7, and a 48. And if we do what we did for median, start crossing them off. Top and bottom are gone. 1 and 7 are gone. 2 and 6. 3 and 5. I missed one, didn't I? Where's my error? The median should be 3.
I got 3.
You got 3?
Yeah.
What extra number do I have floating around here?
4. No, there are 2 4s, isn't there? 7.
There is a 7.
There's 7.
I'm losing my mind, aren't I? Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, that's 12 calls.
You might have crossed 48 like individual numbers.
I probably sure did do that. Well, anyways, when we get down here, it should be between 3 and 4, yes?
Yeah.
Okay, so we average those two together. So we would have 3 plus 4 divided by 2, which is 7.5, or sorry, 7.5 or 3.5. The math is mathin' today. So question, we have X bar, that's our average phone call, and we have our median phone call. But let's think about the actual number of calls she made. You have this extremely long phone call, probably to her mom, it took 48 minutes. Is that pretty typical? To have, look at this dot plot. All of the data is down here, and then you have this one guy over here. If the average phone calls was 7.3, that puts the average right here. Is that even near where all of the bulk of the data is? No, but if I look at the median 3.5 is going to be like right here. Is that more representative of the actual data? That means that the median has resisted that one really large extreme data of 48 minutes. But the mean was very much affected by it. So mean is not resistant, but median is generally resistant, which is pretty cool. We'll stop here before lunch. We'll pick it up after lunch. We've just got a little bit more for today, and then you'll be able to practice. So continuing that thought process, we get this main idea right here about skewed distributions. So in the previous chapter, we talked about the symmetric or bell curve being a bell curve, lack of a better word. And in that case, the mean and the median are generally equal, okay? However, if we have a skewed left graph, which means we have a tail on the left side, our mean is going to shift to the left, and our median will shift to the left, but not as much. So we can see the difference in the distance or the value of the mean and median for skewed left. The mean is going to be smaller than the median. If something is skewed right, means we have a tail on the right side, the mean is pulled more to the right. That's a larger number, so the mean is going to be bigger than the median. Okay? In our bell-shaped curves with skewed data, that's going to be the relationship between mean and median. The data in Table 5, for example 6, represents the birth weight in pounds of 50 randomly sampled babies. The frequency histogram below shows this data as well as the mean and the median for the data. So to keep us from having to type 50 data points in our calculator, I went ahead and did it for you. This is why eventually Excel is going to be a lot nicer for us. And we see this histogram, which we learned about in the other chapter. It is bell-shaped-ish, correct? Somewhat. So this is a bell-shaped distribution, also sometimes called symmetric. It is generally about the same on the left and the right. For one of the skewed graphs, you're going to see a longer tail or a more dramatic tail, or maybe like, an extra point over here that gets bigger again. That's going to be skewed that direction. So in which case, which measure of central tendency better describes the typical birth weight? Would we rather report median or report the mean? So if it's bell-shaped and it's symmetrical, what does the box right above this say the relationship between mean and median are? They're approximately equal. So we know that X bar would be approximately equal to the median. That's what we know from something being bell-shaped, is that the mean is approximately equal to the median. And since these are so close, so since X bar is approximately equal to the median, we're going to use the mean. Now, why would we want to use the mean? Great question. So glad you asked. The mean uses all of the data instead of the position of the data. So that means it's a more accurate depiction, as long as it is not skewed, since it's not a resistant data, of the entire population. So we would use mean, just to write a little bit more for us, since it takes all the data into account. Not just the position of the data. However, if we had a skewed graph, we would want to report the median as the best measure of central tendency, because the mean would be affected by those extra large data points. So we have to start making decisions on what's the best way to report our data without being misleading to the people who are reading our conclusions. Now there's one more measure of central tendency we're going over today. You can probably guess it. So we had mean, we had median. What came after that?
Mode.
The mode. Thinking back to 8th grade, when you learned about the mode of a data, the mode of a variable is the most frequent observation. Mode most. Mode most. The most frequent observation of the variable that occurs in the data set. A set of data can have no mode, one mode, two modes, which is called bimodal, or three or more modes, which we call multimodal. However, the mode is not usually reported if it's a multimodal mode, because that's not like helpful data. So like if every data point was represented 2 times and saying it's multimodal of all of those points, like that's not helpful. So really no mode, 1 mode, or 2 mode are what we're going to report. Once it gets more than that, it's not really that helpful. But in a distribution, this is what 1 mode would look like. Okay, you have 1 value that happens the most. In bimodal, you have this value happening twice, so it's a bimodal graph. Simple enough. Let's look at example 7. It says the following data represents the number of O-ring failures on all space shuttle flights prior to the fatal flight of the Space Shuttle Columbia that occurred on January 28, 1986. So we have all of these number of O-ring failures from the different shuttle flights. Find the mode number of O-ring failures. I think it's pretty obvious here. What is the mode of this data? 0. Just to show some work here, so if you're looking back later and confused on what we did, there were 17 zeros in this data. There were 4 ones. There was 1 2, and there was 1 3. And so it's very clear to us that the mode is 0. Because that is the data point that occurs most often. Example 8 asks us to find the mode of the exam score data listed in Table 1. I'm not going to flip mine closed, but you guys flip your page over to Table 1. That was the example with the score from the tests at the very beginning of the chapter. It says find the mode of the exam data. Look at all of those exam scores for the 10 people who took that exam. What score occurred the most? Maybe let me rephrase the question. Are there any exam scores that are repeated? No. So since we have no exam score repeated, we have no data that has occurred the most because they all occurred the same amount, which means this one would have no mode. So that's always an option. Now, it's important to point out that we cannot determine the mean or the median. So that's what we did on the other pages, the mean or the median of data that are nominal. And if we remember our ranks of data, nominal was the one that was just like categorized with no ranking system. The only measure of central tendency that can be determined for nominal data is the mode. So if we throw it back to our PT example from, I don't remember what chapter, the data in Table 6, remember this one from when we did the frequency distribution, represents the location of injuries that required rehabilitation by a physical therapist. Determine the mode location of injury. Now, this would be very helpful if we had our frequency distribution, but since we've already done that once, let me help you make a quick chart here. The hip occurred twice. The back is on this list 12 times. The hand is on this list twice. I wrote the number 1 and 2. 2. It's 2. The neck appeared on the list 1 time. The knee appeared on the list 5 times. Shoulder 4. Wrist 2. Elbow 1. And groin 1. So out of this list, which location is the mode of this data? The back. So the mode for this data is the back. That is the most often occurring injury seen by this PT. This is the only measure of central tendency for nominal data that we're going to be able to do. The rest of them do require some sort of ranking system or numerical value to be able to determine measures of central tendency. And that's our first lesson in Chapter 3, all about mean, median, and mode, things we've learned about before, but we're putting them in context of a statistics class instead of just 8th grade math. Next class, we'll start to study measures of dispersion, which is going to complicate the things we can do with data and how we can talk about the data. But for today, mean, median, and mode.